Hello, physics kids. Well, we want to go over electric number 2. This is the second part of electricity, and let's start. We want to talk about how we talk about electric fields, okay? So let's do a few things with that first. So if I have, say, a charged sphere here, and let's say it's negatively charged, we want to talk about the electric field. Let's talk about the electric field at that location. Well, how are we going to measure it? Well, unlike a gravity field, the electric field can be both attractive or repulsive. So the very first thing we have to do is, are we going to use a positive test charge or a negative test charge? That's going to determine its attractiveness or repulsiveness. Well, physicists have agreed to use a positive test charge. So if you want to know the electric field direction, just put a positive test charge there. And it is clearly being attracted. So the electric field is going in to a negative charge, but that's nothing to memorize. The only thing to memorize, and you really need to, is that it's a positive test charge. All right, well, let's talk about that. How much is that charge?
Georgina Scardino, please dial 1100. Georgina Scardino, 1100. Thank you.
Yeah. How much is that charge going to be pulled in, right? Well, let's see. How much is that charge going to be pulled in? Well, let's say I put 1 electron there. All right, it's not going to be pulled in. It's going to be pushed out in that case. But if I have 1 electron, it'll be pushed out a little bit. What if I have 2 electrons? It'll be pushed out more. 3 electrons, even more. 4 electrons. You see where I'm going on this? That I'm not trying to talk about what happens just on this test charge. I want to talk about the thing that's causing the electric field. I just want to start describing that electric field. So I have to come up with some way of normalizing for the fact that you might have different amounts of charge on the thing that is being attracted or repelled, and that'll change the force. So the way we do it, the way we define electric field intensity, first of all, it's called E for electric field intensity, equals the force, and that'll be in newtons, the force that it feels. All right, once you put in newtons, divided by the charge on it. That way, if it has twice the charge, we understand it's going to feel twice the force. 3 times the charge, 3 times the force. That makes sense. But you have to put the charge down somewhere, because otherwise your electric field intensity just depends on what you're measuring it with. And that, ladies and gentlemen, makes no sense whatsoever. So F over, you measure charge, the variable is Q. And the units would be in coulombs. So the electric field intensity is given as force per charge. That makes sense then. You normalize it in terms of how much force would 1 coulomb feel, right? And there you go. So we've made sense out of it. But we could do more with this, and more is what happened with this. So let's just talk about the electric field between 2 parallel plates. We want to get this idea to you. So the electric field between 2 parallel plates. Why do you care? We care because 2 parallel plates have a goofy thing happen. Let's have a parallel plate here, parallel plate here. Now, I'm going to ask you a question that almost everybody gets wrong. So see if you could get it wrong too. Then you know you're everybody. All right? It's positive on the top. Negative on the bottom. So the question is, which direction would an electron be pulled, and which direction is the electric field? Seems like a simple question. So an electron sitting here would get pulled which way? Well, it's going to be repelled by the bottom, attracted to the positive on top. An electron would be pulled that way. Great. Which way is the electric field? Well, the thing is, when offered, a lot of people will say, well, that's the electric field. Remember what we use to measure an electric field? Is it a negative charge like an electron? No, it's a positive charge. So if you put a positive charge there, you realize, oh, the electric field is actually going down in this case. So don't remember that when you're seeing that question. It's almost an abusive question, Not now. Now it's just fun to see if you remember. So in this electric field between two parallel plates, the thing is, it is a perfectly uniform electric field. Now, what does that mean? Well, if I have a charge at location 1, location 2, and location 3, let's not just talk about a charge, let's talk about an electron, okay? An electron sitting here at location 1, location 2, and location 3. Which electron is pulled up the hardest? And you might tend to say, well, the electron may be down here because it's closer to the negative charge, is repelled harder than the one in the middle, or the one up here is attracted harder than the one but it turns out, because it's a uniform electric field, this, and this, they all, everywhere in there has exactly the same amount of attraction up or every electron would have the same amount of attraction up in that field. It's a uniform field. So we can use it to mess around with things. And indeed, this is how Milikan's oil drop, famous Milikan's oil drop experiment, was done. Check this out. All right, we wanted to know what the charge was on a single electron. Now, electrons are tiny and they have really, really, really small charges. Nobody knew what a single electron's charge was. All we knew was that a vast amount of them, you could do certain things, so we called a coulomb, before we knew how many actual electrons were in a coulomb. We just knew that amount of charge would have this effect. But we wanted to know how much charge a single electron had. So we used this experiment. Milikan injected oil drops into this experiment. Now he very carefully did work and he discovered what the mass of each oil drop was, and that was not an easy task. We're going to magnify the oil drop and just talk about it for a second. So it's all going in between these parallel plates, but here's the oil drop. What's pulling it down? Well, what's pulling it down, of course, is its weight. So its weight is going to be mass. It's mass times gravity. What's pulling it up? Well, we know a force is pulling it up, and the force has to be from the electric field. If we remember the equation, E equals F over Q, force per charge, right? If we solve that for force, we know EQ equals F. So that F we turn into E times Q. Well, the electric field between the plates was known, Q. The actual charge on the oil drop, that was not known. So Milikan laboriously worked it out. Look at what the equation comes to, though. Q, if these things are balanced, we have mg equals EQ. If we solve for Q, mass times gravity divided by the electric field is going to be the charge on the electron. Let me show you the results, or a sampling of the results that were attained with this. See if you can figure it out. This is just some of the results that would have been obtained, okay? 4.8 times 10 to the minus 19th coulombs, okay? 3.2 times 10 to the minus 19th coulombs. I'm not seeing much of a pattern. About 6.4 times 10 to the minus 19th coulombs. And he's getting all of these a bunch of times. He's getting a 1.6 times 10 to the minus 19th coulombs. He's getting an 8.0 times 10 to the minus 19th coulombs. He's getting a 9.6 times 10 to the minus 19th coulombs. And he's getting all of those a bunch of times. Do you see the pattern? Do you see what Milikan saw? What's the charge on a single electron? Turns out this was the smallest number he ever got. And look at all the other numbers based on that. Well, that's twice as big, isn't it? 3 times as big. 4 times as big. 5 times, 6 times as big. So what's the charge on a single electron? If it's multiples of this, that must be because the oil drop had multiple electrons on it. The smallest possible charge was when it had a single electron on it. So the charge on a single electron was rapidly understood to be 1.6 times 10 to the minus 19th coulombs. That's the charge on a single electron. All right? That's also, if you take the reciprocal of that, that's also where they realized there must be 6.25 times 10 to the 18th electrons per coulomb. It all goes together. So that's where they figured this stuff out. It's pretty cool stuff, isn't it? All right, so that's the essence of electric number 2. The problems associated with it are very simple once you use the equations. Given's formula S and S puts things together for you. If you have, say, a question where you have, look at this, you have this sphere and, right, and you're having some relationship like this. How would you determine which sphere is positive and which sphere is negative? Very simple. Just put a positive test charge right in the middle. Well, if the positive is being attracted to that and repulsed by that, that makes this positive and that negative. Check your work. Does that work? Sure it does. Positive test charge there. Sure it does. Everywhere. So all you do is put a positive test charge. You can figure that right out. Got it? I hope so. If not, hey, watch it again. Thanks for watching. Have a good day.